Okay, so today we'll be discussing the last lecture of CS224. This is this is more about what we can expect to happen in the coming years and how the research in NLP has progressed over the past few years. So let's get started. So what was the scenario of NLP 5 years ago? So there were no sequence-to-sequence models 5 years ago. So right now, sequence-to-sequence are the kind of architectures that have really pushed the progress of NLP forward. So 5 years ago, they were not there. There was no attention. And we also didn't have the large-scale data sets that we have at the moment. And TensorFlow and PyTorch, that was also the time when we didn't really have libraries like TensorFlow, PyTorch, or maybe that was the time around which they actually they started. So that was the kind of scenario we were in last 5 years ago. So now what can we expect in the future in the area of deep learning and NLP? One is making use of unlabeled data. One of the bottlenecks that we have with training large models is the availability of labeled data. So if we are strictly dependent on supervised learning, then we need the data to be labeled. But if we can come up with methods that can leverage unlabeled data, which is in fact available in which is much more than that of labeled data. So that would surely give us a lot of progress. And there's something called back translation that we can use for unsupervised machine translation. We'll see a little bit about that in the coming slides. And unlabeled data can also be used for scaling up pre-training and models like GPT-2. And another area where we can expect some progress in the coming years is the risks and social impact of NLP technology. So when models like BERT and GPT-2 started coming up, there was a lot of discussion about whether these models need to be should be made openly available to everybody or not. And there were people both against open sourcing such models, and there are also people who believe that these kind of research work has to be open. Only then we can move forward with it. So why is deep learning so successful? So on the top here we have statistical learning, and then we have neural networks here. So when it comes to neural networks, one thing that has been tried out to give whenever higher performance is required, one thing that is obviously tried is to add more layers, or in other words, to put it in other words, it's like increasing the number of parameters of the model, and that has in most cases given us better results. So with neural networks, it's easier to get higher performance by increasing the number of layers and by increasing the number of model parameters. So the plot here shows the difference between neural networks and the other approaches. As we can see here, as the data size increases, the model size also increases. That's something we know. So as we keep increasing the data that the model sees, we see that the performance of the model increases when it comes to neural networks, whereas when it comes to other approaches, it's not really so. So right now, what we have is, as long as we keep increasing the model, as long as we keep adding more and more data to the model, and we increase the size of the model. So what exactly does increasing the size of the model mean? That's nothing but increasing the number of layers or the number of parameters of the model. So as long as we keep scaling these two parameters up, we see that the neural networks keep giving us better results. But here, the red dotted line, what it indicates is that around 1980s and 90s, we didn't really have the kind of data or the computation resources that we have right now. That is why even the neural networks existed back then, the limited availability of resources and data didn't really accommodate the progress of neural networks. And that is why the dotted line here indicates that at this point of time, the accuracy is pretty much stagnant. We didn't really have the scope to improve the accuracy because the amount of data and the amount of computational resources were pretty limited back then. But now we are at the luxury of having more data and having a lot of computational resources. Right now, we even have hardware that is being specially designed for helping with deep learning. So the deep learning success actually began in computer vision, and that happened much before the progress that has come in NLP. So we have image recognition things like we have ImageNet when it comes to computer vision, and then we have seen deep learning being successful in machine translation and also in gaming as well. So yeah, so we have seen how deep learning has pushed forward the progress in computer vision, and we have seen how machine translation also uses deep learning. Like Google Translate is now totally driven by neural networks, and even in game playing, we have deep learning that is being used. So when it comes to image recognition, one of the datasets that is dominantly used is ImageNet, which has 14 million examples. And machine translation, the dataset WMT has millions of sentence pairs. Like sentence pair here means for the given same sentence, we have it in multiple languages. And when it comes to playing games, we have for some millions of frames that are collected for some Atari games for training the Atari AI models. So all this indicates that deep learning is very dependent on the number of training samples that we can provide to the model, and hence we have these data sets which are huge in number. Okay. Yeah. So when it comes to NLP datasets, even when we are talking about datasets that are in English, we have for these datasets have like 100K or less labeled examples. We are talking about labeled examples here. If you're only talking about examples like text corpora in some or the other structure, then we'll have much more amount of data. But the amount of labeled data available is much lesser than the total amount of data out there. So, and this is what we have when it comes to English. And if you're talking about other languages, then the amount of labeled data is much lesser. And there are like thousands of languages out there. Even though we have right now the be it machine translation or any other kind of NLP tasks that we are able to do with the help of computational models and machines, they work well for some specific set of languages, but to make them generic and to make them available for people across the world from different countries and regions, we have to come up with methods that can make the same thing possible with with more languages, if not all the languages on planet, because there are thousands of languages, and there are like hundreds of languages which have 1 million or more native speakers. And when it comes to English, only 10% of people speak English as a first language. So there is a genuine need for coming up with methods, or call it data sets, to support other languages. Only then we'll be able to put these technologies to good use so that they can serve people from different regions, not just for specific regions. So the increasingly popular solution for this is to use unlabeled data. And the reason why it's popular is because while it is comparatively easier to collect a data set when your target language is English, it's not the same when your target language is some other language. So let's say if you want to do something like machine translation for a language which is not that popular, And the chances are that the amount of data available for that language would surely be much lesser than that of English. And also, the amount of work that is already done in that language would be much lesser. So it's like in a lot of cases, you might even have to start from scratch. So instead of going with that approach of collecting the data, labeling it, and then using it, we better come up with some other methods to leverage the unlabeled data and come up with some solutions. So using unlabeled data for translation. Acquiring translations requires human expertise. So we have a lot of data sets. So a lot of human effort and manual human effort is involved in the preparation of such data sets. Now, to do that on scale for thousands of languages is not really practical. So if having a source and target language pair for our mission translation task is the only way of achieving it, is the only way of doing mission translation, then we'll have a big problem being able to do that for other pairs of languages, because we may not have the data available and we may not even have the human efforts ready for such tasks. So that is why we have to come up with some methods to use unlabeled data. So separately train encoder and decoder as language models. So what do language models do? They take some set of words and they try to predict the word that comes next. So what we're doing here is we have a word called I. If I is the word, then the possible word that would come next is saw. So I saw a big, so something like that. So here on left we have the sentence in one language, and then we have on the right we have the same in we have it in some other language. So one way of doing this is we separately train our encoder and decoders as language models. But another way of doing it is to train jointly on bilingual data. So that's another different approach that we can try. Yeah. So here's the difference. Like if the task is to translate English to German, what we have in red is when we use a pre-trained model, we see that we get a better blue score is reported. And when it comes to when the model is trained using no pre-training, we see that the scores that are reported are lesser than that of the pre-training. It's not a surprise, as we do know that pre-training helps in giving better results than starting with random weights. Yeah. So what we can do is we have tons of unlabeled data. One way of using that is to make some people sit on it and manually label the data. That's one way of doing it. Or we can take a mission translation model, which is trained on some set of labeled data, and we give our source input to it, and then it produces some output. And then the unlabeled data, it might contain noisy training examples, but still we can use that for training mission translation model on much larger text, which is unlabeled. Yeah. So here what's happening is that we have two mission translation models that are going in opposite directions. So what exactly does opposite directions mean here? So we have a sentence called I travel to Belgium, and we pass it to a mission translation model that converts the sentence in English to French, and then we get the output sentence, which is the French translation for this given English sentence. Then what we do is we take these two things together, and then we pass it. We use this English-French sentence pair to train our French to English model. So this is how we can somehow use the output of one machine translation model to train the opposite model. Like at the top, we have English to French, and the output that is being generated is being paired with the input that is provided here. And both of them together will form a source and target translated text example pair. And that is being passed to the opposite. While we have at the top English to French model, here we are trying to train a French to English model using this as our training sample. So normally the training sample that we provide to the model comes from some data set, but here, as we can see, the training example sorry, the training example pair that is being passed to this model here. So the source sentence is the output that comes from the previous model, and the target sentence is nothing but the input that is given here to the model. So this way we can reduce some amount of human efforts that are needed by using unlabeled data. So here's what this is what back translation is, by the way. So here are some results that are reported. So when back translation is tried on some 4.5 million English-German sentence pairs and 226 million monolingual sentences, you can see here that the model here, which is transformer with back translation, has produced much better scores here, 35 when compared to the previous best, which is 29. What if there is no bilingual data? There is a possibility. Now, if you're talking about something like English and French, the chances are that we already have some data on it, but that may not be the case for every language pair. So what if we don't really have the bilingual data? Unsupervised word translation. So we know that when we have word embeddings, what they do is they tend to cluster together. Like the words that are similar to each other, they occupy some part of the vector space which being close to each other. So cross-lingual word embeddings is an interesting concept where we have I think this is as we can see here, we have some English example words which we can see in blue. And then we have similar words in another language. I think it's German. So what we see here is that what cross-lingual word embeddings give us is that for the kind of embeddings they generate, they tend to generate similar embeddings for the same word, but for different languages. So that's what we see here. So we have the word crisis here. If you can see the place where I have my mouse pointer. So we have the word crisis, and then we have another word which is similar to it, but comes from another language. So how exactly will this help us? So let's see that. Yeah. So we have seen this in the very first lectures of this course. What word embeddings do is they tend to occupy, like the words that are similar to each other occupy nearby spaces. So as we can see here, we have the words that represent some sort of relations here: sister, niece, aunt, brother, uncle, nephew. And then we have some gender mappings here: man and woman. So word embeddings somehow map this sort of information in the vector space. So when we are trying to get the word embeddings for the same words but from different languages, these word embeddings, the structure has to be similar across different languages. So here we have X and Y. We have the word embeddings for words, some of the words here in English. Then we have the word embeddings for the same entities, but in a different language. So as we can see here, first we generate, using word2vec, we generate the word embeddings for both the languages, X and Y. And then there's something called matrix W. You can just think of this as some weight matrix. which the model has to learn in order to map the same words that come from different languages uh, in a similar vector space. As we can see here on the right, we have these blue and orange data points that are overlapping over each other. That means for if there's a word like cat in English, whatever it means in another language, it has a very similar embedding in both the languages. Yeah. So here, what we're doing is this is a very similar structure that we are familiar with, the encoder and decoder. But here, instead of using the regular single language word embeddings, we are using cross-lingual word embeddings. So what happens here is that we this way, even when here we have the sentence "I am a student," and which is being translated into French. And then I should show on the next slide. So here, yeah. So what this sort of model should do is that it needs to have the same representation both for both the sentences. Like it's the same sentence, "I'm a student," which is in different languages, but when it comes to the vector representation for this, by using cross-lingual word embeddings, we get similar representation for both the sentences, though they come from different languages. So another task is denoising autoencoder. So here we have a sentence that is scrambled. Instead of "I am a student," what we have here is "I a student am." So we can use unsupervised neural machine translation for correcting these kind of sentences. So when the encoder takes as input a sentence like "I a student am," and then what we get is "I am a student." So this is called denoising, and we can do that using unsupervised this kind of architecture. So back translation, again, we have seen this in the previous slides. Yeah, so this is an interesting slide. So what exactly is happening here? When given a sentence like "I am a student," and we have this, the language model learns this from the decoder. But what if instead of giving uh, an English sentence as the input, what if we give it in, if I'm not wrong, I think this is French. So let's assume that this is French. The advantage of using cross-lingual embeddings is that since the cross-lingual embeddings give us similar embeddings for the same words that come from different languages, even if the input to this model is the one that we have here at the bottom, sorry, here, what we have here, this instead of the actual English sentence, the model can still come up with this because the cross-lingual embeddings has information for the words in multiple languages. So that way, the cross-lingual embeddings can be used. So yeah, so here at the top we have an English input to the encoder, and then the decoder tries to come up with this. And at the bottom here we have the same sentence but in a different language. And since this is yeah, but still we can see that the model can was able to come up with the same output. So the objective here is to have language agnostic representation. So what exactly does that mean? So here we have a sentence called "I am a student," and when we pass it through an encoder, it gets its own vector representation. And now the advantage of using cross-lingual embeddings is that when we give the same sentence but in a different language, the vector embedding should remain more or less the same. So that's the goal. Yeah. So as we can see here, the encoder vector representation for both these sentences, which are the same sentences but in different languages, they need to be the same. And that is possible with the help of cross-lingual embeddings. Here is a plot that shows how the models that are the unsupervised models do. As we can see here, they're not really as good as supervised models, and that's kind of expected. But it's not like they don't work at all. But as we can see here, they do work, but they're not really as good as the supervised models. So here's another example of attributing. Yeah, so we are talking about methods which are not really being used as the state-of-the-art methods in any real-time application, like using unsupervised unlabeled data. So that's not something that we use at scale. These are more like areas of research, trying to do some experiments, explore, and see what kind of results we get. And while these things could be tried with for things like for languages like English, French, and German, because these are kind of similar, we can at least see that, as we have seen in the previous slides for the word embeddings, the word crisis has similar alphabets in German as well. So as long as the languages have some kind of commonality, I think that is possible. But if you're talking about languages which are purely different, and then it's totally it doesn't really work that well. So here's an example for cross-lingual BERT. So what's happening here is that the input that is being given to the transformer here, it is being masked. Like some of the words are masked, and the model is expected to fill in the blanks. So here we have a mask here, which means the model doesn't know what exactly comes here, and then it thinks the word take is the right word for it, like take a seat, which makes sense. It's semantically correct. Then we have here, and we have another mask here and here, and the model comes up with words like have a drink, now relax, and we have now here. So what we have at the top is what a regular BERT model does. By using a cross-lingual model, what we can do is, even when the model here, as we can see, the first few words are in English here, which is followed by words in some other language. But if this transformer model is given cross-lingual embeddings, then it can come up with words which are from different language. That surely is a big advantage of using cross-lingual embeddings over the regular embeddings. So now we'll see a few slides about huge models and GPT-2. So here are the parameter comparison for different models. If you're talking about LSTMs, they have like 10 million parameters. If you're talking about Elmo, GPT, they are close to 100 million parameters. And BERT has like different sizes. It comes small, large, and those kind of variations. So BERT large has some 320 million parameters, whereas GPT-2 has 1.5 billion parameters, which is huge. So there is something. A honeybee brain, which we're talking about, a living being here, has close to 1 billion synapses. So here is a comparison plot, like the number of the time it takes for training these models. As we can see here, right down here, in 2013 we had AlexNet, and then somewhere in 2015 we had it VGG and sequence Seek to Seek, GoogleNet, and then in 2016, we had ResNets and deep speech, which is used for speech recognition. And then we have other models like exception, neural machine translation, AlphaZero, AlphaGo Zero, etc. So as we can see here, as the training effort or time it takes for these models is so different. In 2013, what the models like AlexNet needed is much lesser than something like Exception, which came 4 years later. So as we can see here, as for with every year, the amount of the models got bigger and bigger, and the amount of time it takes to train these models also gets longer. Okay, so now this is about GANs. So it's here are some examples of some photos that are generated using GANs. And there is this website called thispersondoesnotexist.com. I'm not sure whether you have come across this or not, but it's a website where if you check the website, you see images of people's faces who don't exist. So they are totally generated by some GAN models. So huge models in computer vision. So these are all some architectures or models that are used for computer vision. As we can see here, what we have on x-axis is the number of parameters, and the y-axis reports the accuracies for different models. GoogleNet right at the bottom here has something like 0.75% of accuracy. Compared to that, the ResNext 101 has close to 80% accuracy, but we also see that the amount of parameters that increase from GoogleNet to ResNext is almost like 10 times. So as we have bigger models, they surely give us better accuracies, but they come with much more number of parameters. So if we have to train these huge models, the normal single GPU machines wouldn't really be able to handle that amount of computation. So what we have right now is model parallelism and data parallelism, where you tend to train your model using multiple GPUs instead of single GPU. And the same goes for data as well. Like if you're talking about data which is like 1 GB or something, you can simply use a single machine for that. But whenever if you're talking about machine translation or anything of that sort that is being used by organizations that like Google, which support millions of people, then those models are trained by data like 40 GB or 50 GB, something like that. So that is not really practically feasible to do all of that using a single machine. So we do need parallelism. And so there is also a lot of research that is happening in the area of hardware. We now have some things like TPUs, which are exclusively being developed for supporting the neural network model training. So GPT is a really big transformer language model. So language model is nothing but given some set of words, it tries to predict what comes next, which means that can be used to generate text. And that's what GPT has been used. So it's trained on 40 GB of text. So when we're talking about text, which is this big, we should not only worry about the amount of computation that it takes, but also the amount of efforts it takes to make this data model ready, training ready. So we have to make sure that whatever the data that is being given to the model is of good quality. So that itself takes a lot of effort. And so all of this data was collected from web pages, from Reddit links. So what exactly can we use this model for? One thing is for language modeling, which is text generation. And we can also use this for for getting the perplexity scores of different data sets. So we have all these data sets, and when we have a model that is trained, when we have the GP2 model, we can use that and we can get some sort of benchmarking results, the scores for all these different data sets. So GPT can also be used for zero-shot learning, no supervised training data. So we can use that for language modeling, as discussed, to generate text from a prompt by giving it nothing, and we can also use it for other tasks like reading comprehension, summarization, translation. So let's talk about translation here. So in GPT, as we have seen in the previous slide, normally when we are training a model for performing machine translation, we have to say that, okay, here's a sentence which is in English, and here is its equivalent in French. So we give that source and target language pair to our model, and the model learns how to map the source language to the target language. But here, when it comes to GPT, we haven't really given data in that format or structure, but still GPT was able to do machine translation. It may not be as good as the other models which are trained on machine translation data, but it was still able to get some translation done. So how exactly is it able to do that? So yeah, so how can GPT-2 be doing translation? That's because GPT-2 is given big corpus of text. Now in that text, we might have examples like, as we can see here, there might be a sentence in some other language which is not English, and then which is immediately followed by its translation in English. So since GPT-2 is trained on huge corpus, which might include uh, many such examples, it is also able to get some mission. It can also be used for mission translation, and then for question answering as well. So again, here nowhere GPT-2 is not exclusively trained for question answering, but it was still able to do it. It's like when compared to simple baseline, which only gives 1% accuracy, the GPT-2 model gives 4% accuracy. Here are some examples. These are like cherry-picked, selectively taken. So here are some questions, and here are the generated answers. These are all correct. We're only seeing results here which are correct. So what happens is models get even bigger. So as we can see here, for some tasks, like for reading comprehension, we see that as the number of parameters increase, we see that the score keeps on increasing. So how many parameters does it take for a model like this to perform at the same level as that of humans? So humans reading comprehension score is 90, and to reach that level, the model's parameters should be 1 trillion, which is huge. Yeah, so what was the reaction for GPT-2 like? So you must have come across this after OpenAI has announced that they're not going to release the full model, but they have decided to only uh, open source a much smaller version of the GPT-2, because they don't really want to take a chance and make this available to people who could put it to some bad uses. So there was a lot of discussion on this when this happened, when OpenAI announced this. And I did come across this Reddit post at that time. So when OpenAI said that, then they're worried GPT could be used for some uh, for unwanted applications. And then someone said, like, should I release my MNIST model or keep it closed source, fearing malicious use? So And here we have someone saying they should open source the language model, whereas here's another argument which says that it shouldn't be released. So what are the arguments for and against the release of the full GPT-2 model? One, as we can see here, the arguments on left say are reasons why it needs to be released. One thing is that this model isn't much different from existing work, which is true. Like it's not like GPT-2 is something which is totally new from the existing or the previous work. So it's not so different from the existing work, and not long until these models are easy to train. So if OpenAI didn't release their trained model, it's somebody else might do it. Like it is possible given the cloud availability that we have right now. Somebody else can do it. And so we have another example, Photoshop. So it is possible to do a lot of things with Photoshop, but that doesn't mean that everybody is doing it. So there is a tool out there which is available, which could be put to some malicious use, but it's not like it is happening all the time. So that's another argument saying that that can happen with GPT-2 as well. Like even if you release it fully, it's not like it is only going to be used for some malicious purposes. And the model has to be released so that researchers can study it. And there are several other reasons as well. And let's see now why some of the reasons why models like this should not be released. One is danger of fake news, news comments, etc. So the kind of text that is generated by GPT-2, it's not really easy to differentiate whether it's a real text or a generated text. So that's one problem. Like if you're not really able to distinguish between real and generated text, now that could lead to a whole lot of problems. Yeah, so even if this model isn't dangerous, later ones will be even better. So which means the models that follow this could be even more dangerous. So who exactly should make these decisions? Should the experts on computer security decide whether these models could be openly released or not? Or the technology experts or the society should decide it? What about, or maybe the experts on ethics should decide? So these are open questions. Like I think these are kind of things that we do have to think about when we are working or researching in this area. Moreover, it has to be a personal responsibility to make sure that whatever the work that we are using, it is only for, it has to be put to good effect. And if there's a possibility that something could possibly go wrong, then we have to make sure that it is avoided. And another thing that it's something that is not really talked about is regulation. So it's not really easy to regulate technology. Like anybody who sits in front of the computer at their homes can come up with something, and it's not really possible to regulate all of it. So even if it is possible, and then there will be this argument of whether to regulate it or not, because then it's like putting restrictions on research and experiments. So these are the things that should be left to one's own personal responsibilities and ethics. And need for more interdisciplinary science. So it's not just deep learning, but technology is like it has spread into almost every other industry. So it also calls for a need to make this interdisciplinary. The more the people we have who come from different backgrounds and different disciplines, the better it is. Many are the examples of NLP with big social ramifications, especially with regards to bias and fairness. Yeah, so bias, that again, it's like we have discussed that in the previous lecture, that itself is it's a thing on its own. So when we're collecting all the data, how exactly can we avoid bias that could come with it? High impact decisions. Yeah. So we have seen in the previous lecture like how these ML models are being used to decide the risk factor, like what is the possibility that a person who has committed a crime today would commit another crime in the future, and hiring decisions. We now have models that are trained to decide whether the person could be called for an interview or not. Grading tests, the models take the answers that are provided by students, like essays written by students, and they assign a score. So these are all things that are already happening, and which means these are not just some silly applications, because they do impact lives, and they do that at scale. So it is very important that, since these models or these models are being used for applications like this, we have to be really careful with the way we come up with those kind of models. Uh, so can quickly evaluate a machine learning system for some kinds of bias. So we can also use these systems for evaluating bias. If a model is not acting impartially for different data, then that means there is some problem in the data. So we can also use these models to evaluate the data and the bias. However, machine learning reflects or even amplifies bias in training data. So that's something we have discussed. So if there is bias in data, there is every chance that the machine learning model learns something from it, and then it also acts or performs in a biased way, which is not really good. So here's an example. We talked about this in the previous lecture, if I remember. Amazon scrapped secret AI recruiting tool that showed bias against women. So there is this Amazon model that was uh, it was used for kind of filtering people for the interview or the recruiting process, and it is seen that the model is biased against women. And here's another example. So the GRE automated essay scoring system, which uses some sort of model, tends to give a better score or higher score to the text which has which has which has these kind of words. Like if the model sees words which are not kind of usual, and it thinks that, okay, this essay is very well written, and it gives it a higher score. Chatbots. So chatbots is so there is a genuine need for chatbots. It's not just having chatbots which would tell us how the weather is or something like that, but they can really be used for some good causes. Like here, there's something called Warbot, which helps, like you can talk to it about you can talk and feel better. So there are these kind of use cases as well. But the problem is, if we have these kind of chatbots, there is every possibility that they are kind of prejudiced, or they kind of act discriminatively depending on the kind of data that are trained on. So what did BERT solve, and what do we work on next? So these are kind of results with bag of vectors. The scores was 58.6. By using LSTMs with attention, we got score improvement in score by some 5 points. And then attention, when added with Elmo, we got slightly better results. And finally, with BERT large, we have the best score of 80, and which is still behind human score. The death of architecture engineering. So something that we have seen from 2013 till 16 is that, especially in computer vision, the progress was seen because there were different architectures. We had things like AlexNet, we had InceptionNet, we have GoogleNet, and we have ResNet. So these are all different architectures, and every architecture has its own every architecture has given us further improvements in the accuracies. But we are seeing a different trend right now. When it comes to NLP, as we can see here on the leaderboard, the top 5 or so, they're all one or other variants of BERT. So what we're talking about is not different architectures, but it's the same architecture with different variants. So one thing you can do is you can either spend 6 months on coming up with a different architecture design that would give you like 1 point improvement, or you can simply take BERT, make some changes to it, or make it 3 times bigger and get 5 points improvement. So right now, at least the past 2 years or so, we haven't really seen much like in terms of architecture, we haven't seen much happening, but it's more like the same architectures that are being used with some or the other variants. So what really are the hard tasks in NLU? One is reading comprehension. Given a paragraph of like 5 sentences and expecting the model to do well is one thing, when compared to giving text which spans across multiple documents and asking a question whose answer could possibly come from different documents. That's a different task altogether when it comes to the level of difficulty. So reading comprehension is a very hard NLU task, especially when you're talking about longer documents and multiple documents. And one of the problem is that for many of the comprehension data sets, the people come up with the questions, they see the context and they come up with the questions. It's not really realistic. And it can also be that these questions could be easy when compared to, like, it's better to train the model with harder questions rather than the easy ones. So here's another example. I think we are getting close to the time. So there is still a big gap to human performance, as we can see here. For Q&A, the best we have right now is BERT with 2 contexts, and it gives a score of 64.9, whereas human performance is 81. So there's a huge gap there. So there is something called HotPotQA, which is another data set. The difference here is that the questions are over multiple documents. So this seems to be like a much tougher data set than a simple Q&A data set where the question and answers are in like the same paragraphs. But in this case, we have the questions that are over multiple documents. So here again, there are some of the scores here. So multitask learning is another important area of research right now. So when you have models like BERT, which are huge, why not use them for multiple tasks rather than single tasks? So there is something like Deca NLP, which is a collection of like 10 tasks. We have discussed that in the previous lecture. Low resource settings. So like 4 or 5 years back, nobody was really talking about deploying ML models on mobile. But right now, it is not only active, but it is also like very required part. Like if you're coming up with an ML model, it's not just if you are working on some ML problem and it needs like big GPUs to run it, especially for at production, it's not really going to be feasible. So you also want to come up with models which can be deployed in mobile. So for that, we need models that can run on computation which comes as low as the mobiles, and low resource languages. So we have languages like English which have a lot of resources, but when it comes to other languages from other countries, we may not really find as many resources for that. So that's another area as well. And low data settings. So what can we do when we have very limited data? So that's another area where we can expect some interesting work in the near future. Model interpretation. This is another very essential part. Like if the model is doing something, you want to know why it is doing it and how it is doing it. So it's not just enough if the model is doing something as expected, even if it's good, you want to make sure that it is doing it for right reasons. So for that, model explanation and interpretability becomes very critical. And we have seen a lot of progress in this area in the past few years as well. The example, yeah, so NLP is rapidly growing in the area of chatbots for customer service and healthcare. So healthcare is another very important industry where we can use NLP and use it for applications which can really make a difference. The problem here is we don't really have as much health data as compared to the other data, especially the open data is pretty limited. Okay, so that's all about this lecture, and this also ends this this study group. Like, we now have finished the last lecture in CS224. It took longer than I expected. I think we have been doing it for a few months now, but yeah, it was. This is the first time that I have hosted this, and it's a very good experience for me. So is there anything else, anything that you would like to discuss or share, or anything that I missed in this lecture?
Mentioned another class that you were thinking of doing, or it might have been somebody else.
Are you talking about another NLP course that we discussed like a couple of weeks ago?
Yes.
Yeah. So
I forgot, it was from some other university. I'm not sure which one.
Yeah, it's from CMU, I think. Yeah.
Okay.
Yeah. So I can host that as well. So can we start again with a new course? Sure, we can do it. So here's the thing. I'll be busy for the next few weeks. And once I'm done with that, probably in March first week or something like that, we can start another course, which would be based on NLP. I will go through the one that I just mentioned, like CMU. We can take that. That's what I have on mind right now. I'll also check. I think I saved like a couple of NLP related courses. I bookmarked them, and I'll see what content they cover, and I'll be sharing that in the channel in a few days, and then we can have a poll and see which one the people are more interested in, and then we can get started with it. Yeah.
It also, like also the Joseph's covers of fast AI NLP should be like he's going pretty fast, but I think it should be done in a month or so.
Okay.
So that may bring more people into next class.
Oh, sure. Okay. We'll see.
Okay. Well, thank.
Yeah. Thank you for being here. Yeah.
Thank you.
Thank you.
Bye.
Bye. So yeah, I'll post a poll sometime soon, and then we'll decide what we'll be doing next. Yeah. And thank you for joining today and during all the weeks. I had a very good time preparing for these study groups, and I have learned a lot. So thanks to this, and we'll see what we'll be doing next. So thank you. Have a happy weekend, everybody. Take care.
Bye.
Bye.